Hi, in this video of Inkpot, we are going to be starting with the next unit, which is on the systems of linear equations. The first thing that we are going to do is, understand how to calculate the inverse of a matrix. Now, I understand that most of you are familiar with this already, but since this is the beginning of the unit, and inverse of a matrix is extensively used in systems of linear equations, that is why this is what we're going to start with. This will be followed by the calculation of rank of a matrix, and then we'll do a short assignment and move ahead. So let's get started. Now, the first thing to understand is what is the determinant. Now, essentially, a determinant is a number associated with every matrix, and it's not just every matrix, but it's every square matrix. You can only calculate the determinant for a square matrix, the way that you calculate the determinant is using the so for a 2 cross 2 determinant, 2 cross 2 matrix, you know that if this is A11 in A12, A21 and A22, then your determinant is just going to be equal to A11, A22 minus A12, A21, which is exactly what we have here. Now, the thing is that the same concept of calculation of determinant can also be extended when you look at a system of linear equations. So if you have a system of linear equations in two variables, which are x1 and x2, and if it were so to say written in a manner that the coefficient associated with each of the variables is particularly in the order where you have a11 x1 plus a12 x2 and so on, a21 x1 plus a22 x2, then this entire system of linear equations could be represented. This matrix then a11 a12 would actually be the coefficient matrix, as you will learn better in a short while, and the determinant of this said matrix would be precisely equal to what we just calculated. So for a 2 cross 2 matrix, that is what the determinant is given by. For a 3 cross 3 matrix, the procedure is similar, and we'll get to it. But before that, let's just see what a determinant represents geometrically. So for any determinant, essentially, if you plot the 2 points a11, a12 and a21, a22, then the area under this parallelogram is what is the determinant equivalent to. So the determinant value is equivalent to the area of this parallelogram precisely. So that's just something to keep in mind. You don't really need to remember it, but it's interesting. Okay, now we come to determinants of order 3. Now similarly, as we had started in the earlier section, let's just see if you had a system of linear equations which were written in this format, and recall that when I say a11 or a12 or something like aij, it's the ith row and the jth column always. So that's just something to keep in mind. So as I was saying, here you have a11, a12, and you now have 3 variables. This 3 variables and 3 equations in 3 variables would give rise to a 3 cross 3 matrix, the determinant of which can be calculated in the following manner. You have a11, and so essentially you take a11 and you eliminate this row and this column, the first row and the first column respectively, and whatever you are left with, you actually take that and you calculate the 2 cross 2 determinant here. Okay, and essentially to remember whether it's a positive sign associated with a11 or a12, or a negative sign associated with a12 and a positive sign associated with a13, the easier way to remember this is that if the sum of the two ij, so if I plus j is actually odd, then you would have a negative sign, you would have a negative sign associated with it, and if I plus j is even, then you would have a positive sign associated with the determinant calculation. So that's just something to keep in mind. Again, the geometric representation of a 3 cross 3 determinant, just like a 2 cross 2 determinant was a parallelogram, the 3 cross 3 determinant can also be plotted, and it would look something like this. Once again, this is not something that you have to remember. It's just something that is information that needs to be kept in mind. Okay. Now, because we want to determine the inverse of the matrix, let's move from determinants to actually coming to some terminology that we need to understand before you actually get onto the inverse. So the first thing is that what is the minor of a determinant? Okay. Now, in the above example that we had of 3 cross 3 determinants, you had something like, like I had said, you eliminate the first row and the first column to get this particular determinant here. Similarly, for C1, you eliminate the particular column of C1 and the first row, and what you get, whatever you're left with, which is going to be this, portion here and this portion here, you have that as the, determinant to be calculated. So this determinant, essentially the 3 cross 3 determinant that you were you'd begun with, is expanded in terms of minors, and minors are calculated in exactly the manner where, so for example, if you were to calculate A11's minor, you would eliminate the first row and the first column, and the matrix that you would be left with, the 2 cross 2 matrix, would be the minor. Okay. So it is a sub matrix, okay, which is obtained by deleting the row and the column containing the element, okay, given in the 3 cross 3 matrix. So for 3 cross 3, this is how you would define it. It would be defined in the exact same manner for a 4 cross 4 determinant as well. While 4 cross 4 determinants are not something that you're generally asked to calculate, understand that it's the same concept that you might have to use. Okay, so the next term that we come to is cofactor. Okay, and the cofactor of a determinant is defined in terms of the minor itself. So a cofactor is essentially the minor plus a sign attached to it. So like I had mentioned earlier also, if the sum of I plus j is actually equivalent to an odd number, then you would have a negative sign associated with the minor, and therefore the cofactor would be the negative of the minor. At the same time, if I plus j is even, then you would have a positive sign associated, and that means that the minor would be the cofactor would be equivalent to the minor itself. So that is what cofactor is all about. Okay, now the next term that comes in is the adjoint of the matrix. Okay, and the adjoint of the matrix is actually the transpose of the matrix, where aij, alright, is the cofactor of the element aij. Okay, so understand what is happening here. You first calculate the minors of the determinant, or in the minors in general. After you calculate the minors, you actually assign them signs depending upon the value of I plus j. So then you have the cofactors. Okay, and if you were to line up all of the cofactors, okay, as so if the cofactor were represented by capital A, and that's generally how cofactors are represented. So if you had A11, A12, A13, and so on and so forth, you would have a matrix where you would have this as A33 and A22, okay, and so on. So, and this would be A31. Now if you were to take a transpose of this matrix such that this actually becomes A11, A12, A13, and similarly this becomes A21, and so on and so forth, then this would actually be the adjoint of the matrix. So if you look here, this is exactly what is happening. You have A11 and A12, A13, which is this matrix right here. The transpose of this is actually equivalent to the adjoint. Okay, so the first step is the minor, then is the cofactor, then the adjoint of the matrices of cofactors. Okay, So for example, if you were to find the adjoint of this particular matrix, how would you do it? So if you have A11, the fact is A11 is actually going to be equivalent to positive of the determinant of 0 minus 6, okay, and A12 similarly would be so A1 and 2, I'm sorry, 1 and 2, so it would be minus of this determinant, which should be minus 4 minus 0. A13 would be equivalent to 1 and 3, so that would be equivalent to positive of 4 minus 0. A21 would be equal to negative of so the second row and the first column, 1 minus 2, okay, and A22 would be equivalent to the second, and second goes so you would have minus 1 into minus 1 minus 0, and obviously this is positive here. A23 would be equivalent to negative of, so you have the second row third column, 1 minus 0, so yeah, then you have A31, which is equivalent to positive of 3 and 1, so this is minus 6 minus 0. Then you have, I'm sorry, this is equivalent to, then you have A32, which is equal to negative of 6 minus 8, 32, yes. And lastly you have A33, which is equivalent to the third row and the third column, so you have 0 minus 4, 0 plus 4 actually, so okay. So now that you have these, all you need to do is stack the transpose of this matrix and you would have the adjoint. So I'm going to leave you to that. Okay, now we come to the rules of determinants. So essentially, if each of the entries in one or more of the rows or the columns, so essentially if either one of the row or the column is completely filled with zeros, then the determinant is equivalent to 0. The determinant of a matrix is equal to the determinants of its transpose. You can test this out actually, and if you multiply the entire matrix by a constant number, then the determinant is also going to be just multiplied with that constant. Okay, so if two rows or columns of A are interchanged, then the determinant can change its sign, but it will keep its absolute value. Okay, and this is important because if you mess up the determinant value because of some row operations, then you need to understand that you've gone wrong somewhere. The determinant value cannot change. It is absolute in that sense. It can change its sign, but it cannot change the value itself. Okay. And if any two rows or columns of A are equal, then the determinant is also equal to 0. If they are proportional, then also it is equivalent to 0. These things will become important when we are doing other kinds of systems of linear equations, and I'll make that point there as well. But this becomes very crucial when you're dealing with linear equation systems. So if the scalar multiple of one row or column is added to another row, basically if you have row operations, then the value of the determinant cannot change. Okay. And the determinant of any the product of any two matrices is the product of the respective determinants. Okay, so the inverse of the matrix is actually equivalent to the 1 upon the determinant of the matrix times the adjoint of the matrix. Okay, So first, if your square matrix has an inverse, the first thing that you need to check with any matrix is whether or not the inverse itself exists. If it does exist, then the determinant would have to be non-zero for it to exist, and you know that the inverse is defined as a into x is equal to x into a is equal to I, where I is an identity matrix. Okay, and the way you would calculate the determinant is like I said, 1 upon the determinant of a into the adjoint of the matrix. So you have aij, which is this, and you have a inverse, which is adjoint a upon determinant of a. Now if a inverse if a and b are invertible, then you have the following properties, where a inverse is invertible and a inverse of it, the inverse of an inverse is the matrix itself. If AB is invertible, then AB inverse is B inverse A inverse. This is similar to the transpose law, where AB transposed is B transpose A transpose. So you should definitely remember this. Okay, and the transpose of A is also invertible. Naturally, if A is invertible, then the transpose is also invertible, because the transpose doesn't change the determinant value. You have A transpose inverse is equal to A inverse transposed, and similarly C into A transpose inverse is equal to C inverse A inverse, A transpose inverse, or A inverse, whatever. Okay, now this is a particular matrix which you have. You should try to calculate the inverse of it on your own.